Hi everyone, we're going to talk about Chapter 4, Linear Functions today. And if you will recall, we have been talking in depth about functions, but various types of functions. This chapter 4, we will focus specifically on linear functions. In this section 4.1, we're going to cover several objectives. In this section, students will represent a linear function, determine whether a linear function is increasing, decreasing, or constant, interpret slope as a rate of change, write and interpret an equation for a linear function, graph linear functions, determine whether lines are parallel or perpendicular, and write the equation of a line parallel or perpendicular to a given function. So we have quite a few objectives to cover, so let's get started with this first one, representing a linear function. So in order to represent a linear function, there are several ways that we can do this. The first one is representing a linear function in function notation. Now, we just got finished with chapter 3, and you will recall we used function notation for many types of function, not just linear. We had quadratic, we had cube functions, we had square root functions. But again, we're going to focus specifically on linear functions here. So hopefully you will recall sometime in your past, I'm confident that you were introduced to what is called slope-intercept form. This is an equation that is linear. To write this equation in function notation, remember that the output variable is replaced with the function notation. But at any rate, we can represent a linear function in function notation. And again, this is slope-intercept form of a linear function. So instead of y equals mx plus b, we can say f of x equals mx plus b. We'll talk more about this more in depth later in this lesson. Another way to represent a linear function is in words. The train's distance from the station is a function of the time during which the station moves at a constant speed, plus its original distance from the station. The train is moving at a constant speed. So it's changing its distance, which is what we're finding. The train's distance from the station is the function of time during which the train moves at a constant speed, plus its original distance from the station. So because it's moving at a constant speed, that's a rate of change, which is the same thing as a slope. So because it's changing at a constant speed, that makes it linear. Now, looking at this particular scenario in table form, t would be time, and d is the function. So d of t is the train's distance from the station as a function of time. So this is distance from the station. T is time, I'm guessing, in hours. So each point on this table, all of them together represent this particular linear function. So after 0 hours, the train is 250 miles from the station. So what that means is that at the beginning, before the train travels any miles at all, it's 250 miles from the station. After 1 hour, it's 333 hours from the station. After 2 hours, it's 416 miles from the station. After 3, it's 499. And how can we tell that this is linear? Well, check out this. These points are going up at a constant rate. We're adding 1 each time. To the t's. If we were to add to each of the y's, they are going up at a constant rate as well. I believe it's going up 83 every time. So it's going up at a constant rate like if I had this table, the same table, and we had the point 0, 250, and then we skipped the 1. But because this went up 2 and this went up 166, it's still going up at a constant rate because over 2 tries it went up double the 83. So as long as when you check the rate of change of your points, as long as it's going up consistently that way, you're okay. So the points won't always go up consecutively to the next number like this. They can skip like that, but it doesn't mean they're not linear. So you just have to check the rate of change. Basically find the slope from the table, and we will review how to find the slope in a little bit. And as long as the slope is consistent, we're good. Now we can also represent it in function notation, which we talked about earlier. So in this case, it starts off 250 miles from the station. So that's your starting value, or your y-intercept, which is b. And then it's traveling 80 up. It's going up 83 for every hour. So 83 miles per hour would be your rate of change. So that would be this particular scenario, the train scenario, in function notation. Now we can also represent this as a graph, and so this is where you could take the equation and use it to create the graph. You can definitely use the table of values to create the graph. So if you'll look, 0 goes up to 250, and then 1, so that's the point, 0, 250, and then 1 goes up to 333, and then 2 goes up to 416, so on and so forth. And you'll see what they form. They form a line. So linear functions form lines. They go up at a constant rate or a constant slope, and the graph that it yields is a straight line. Sometimes it goes up, sometimes it goes down, sometimes it's flat, but it is a line. So specifically, a linear function is a function whose graph is a line. Linear functions can be written in slope-intercept form, which I just talked about, which is f of x equals mx plus b, where b is the initial starting value of the function when the input is 0 for x, or for whatever the input value is, and m is the constant rate of change, or the slope of the function. And we've talked about rate of change back in chapter 3. The y-intercept is at 0b. Okay, so when we have f of x equals mx plus b, that's saying that the function is equal to the rate of change. This is going to help us for when we're representing it with words. Rate of change times x plus b, which is our starting value. So if we think of it in these terms, rate of change x plus start value, and that is the same thing as y equals mx plus b, sometimes that makes it easier to translate functions that are represented by words into functions that are represented by equations. So we're going to start off with that. So just remember, y equals mx plus b, or f of x equals mx plus b is the same as f of x equals rate of change x plus start value. So that's what we're going to do here. We're going to write an equation for the linear cost of a function. So I'm just going to write f of x is equal to mx plus b. In this case, we're not using f of x, we're using t of n. So mt plus b. And so just to remind you, m is the rate of change. And then b, if you will recall, is the starting value. The y-intercept is the starting value. So if we can think of it this way, it might make it easier to translate this word scenario into a function written as in function notation. So at noon, a barista notices that she has $20 in her tip jar. If she makes an average of 50 cents from each customer, how much will she have in her tip jar if she serves in more customers during her shift? So think of it this way. How much does she start with? What is her rate of change? Those are the things that we need to know. So she starts off with $20 in the jar, and she's going to add to that at a rate of 50 cents. So if we were to fill this in, T of n, so the tips as a function of the number of customers is her rate of change, which is 0.50 times T plus the starting value, the amount that started in the jar, which is $20. And there we go. We have represented this word problem. So this function that is represented with words, we have now represented that same function in function notation. All right, so let's talk about the next objective, determining whether a linear function is increasing, decreasing, or constant. So increasing and decreasing functions, the slope determines if the function is an increasing linear function, a decreasing linear function, or a constant function. So for a function written in f of x equals mx plus b, it is increasing if m is greater than 0. So what that means is the slope is positive. So what you need to do to determine this is if an equation is written in slope-intercept form, we identify the slope, and if the slope is positive, that tells us that the linear function is increasing. If m is less than 0, or the slope is negative, that means that the linear function, is decreasing. And if our slope is equal to 0, if it's 0, then it's going to be a constant function. And let me show you what each of those look like. So this would be a function that's going up. This function would have a slope that's positive. This function is going down from left to right. So this function would have a slope that's negative. And this function is flat, horizontal, so it has a function that is 0. So how do we tell if a function is increasing, decreasing, or constant? We check out the slope. So check out this example. If I had y equals negative 2x plus 5, first you would identify the slope. This is easy because this is in y equals mx plus b form, in slope-intercept form, and we can see that the slope is negative 2. Therefore, it's negative, so it is decreasing. What about y equals 3? So in this case, you don't see a slope we have y equals 0x plus b. B is 3. In this case, our slope is 0. So if you don't have an x term, then the slope is 0. If it's 0, then it is constant. All right, what about y equals 3x plus 1? Well, in this case, the slope is 3, mx plus b, 3x plus 1. 3 is the slope. That's positive. So because it's positive, it is considered an increasing function. All right, and that's how we determine if linear functions are increasing, decreasing, or constant. So calculating slope, again, something that you should have done at some point in your mathematical past. We did rate of change as it pertained to all functions, but slope specifically on a line from a linear function. It's a rate of change. It's represented by the letter m. It can be calculated according to the following. We find the ratio of the change in output to the change in input. So the change in y, delta y, that means change in y, to change in x, delta x. All right. You may have learned it, rise over run. The easy way to find it is to take 2 points on the linear function that you're trying to calculate the slope for and label the 2 points 1 and 2, and then take the second y, the y from the second point minus the y from the first point, and that's the change in y, and divide that by the change in x, which is the x of the second point minus the x of the first point. So this is definitely just like what we did when we did rate of change, except we're specifically looking at linear functions here. So how to, given 2 points from a linear function, calculate and interpret the slope. First, determine the units for output and input values. Okay, so what we mean by that, let me just go back up to the train problem. The output value here, the output value was distance, and the input value was hours. Okay, distance and hours. Okay, so that's the first thing that you do to interpret the slope. Then you actually calculate your m, your change in output values and your change of input values, and you get whatever that ratio is. And then once you do that, you interpret the slope as a change in output values per the change in input values. So if you'll remember, we had d of t is equal to, what was it, 83 t plus 250, and so you can clearly see, you can clearly see that 83 would be in front of the variable. That is our slope. So m equals 83. Now, no, we didn't use points to find it, so I'm just taking it from the equation. What I want to show you here is not how to find the slope with that formula I just showed you. I want to show you how to interpret the slope in terms of the units. So if you will remember, slope is the change in y, change in output over the change in x. So the change in y is distance. That's why it tells you to identify what the units are. Distance, and I'm guessing in miles. So that's the units, is miles. And then x's, that's time. And the units in this case are hours. So we would read this as miles per hour. So our slope of 83 is the distance the train travels. It changes for the function where the distance is a function of the time. The train changes its distance 83 miles per every hour traveled. So for each hour traveled, it changes the distance by 83. So that's what the function means in this case. In this case, that would represent a a speed, that rate of change. All right, so now that we've talked about interpreting it, let's actually just use that slope. So if f of x is a linear function and 4, -1, and 9, 2 are points on the line, find the slope. Is this function increasing or decreasing? So I'm just going to label this as 0.1 and 0.2. And so that makes this point, these coordinates x1 and y1, x2 and y2 there. So if you'll remember, if you will recall, the formula for slope is y2 minus y1 over x2 minus x1, and this should seem really, really familiar, especially if you remember how to do slope, but specifically if you'll remember what we just did in chapter 3, rates of change. So plugging in numbers, y2 is 2 minus y1, which is -1, over x2, which is 9, minus x1, which is 4. So the 2 minus -1 becomes 2 plus 1, which is 3. 9 minus 4 becomes 5. Our slope is 3/5. And don't forget, it asks, was it increasing or decreasing? This is positive. So because it's positive, that means that it is increasing. So we're going to stop the video here, and we will pick up with this next example in part 2.